My name is Sarah Markov. Okay, I'll try again. Hi, everyone. Good morning. My name is Sarah Markov from the University of Amsterdam. I really wish I was there with you. It's probably much nicer weather. But anyway, so we have a very packed morning with talks going from accretion and ejection all the way to relativistic reflection and gravitational waves. And I just want to make a couple logistical points really quickly. So don't forget to put your questions in the Slack and in the channel, session 3. So that's where we're going to be, and I'll be looking and I'll be trying to man that together with Elise and Pop are going to help take your questions. And always try to remember, say your name, because it's hard to see on these little screens for those of us online. So say your name before you ask questions. And one other thing to announce, I don't know if he's here yet, but it's also Dave Russell's birthday. So if you see him, wish him a happy birthday. And with that, let's get started. So our first speaker today is Nathalie Degenaar from also University of Amsterdam, and she's going to be speaking about accretion and ejection connections. You have the floor.
Yeah, thank you, Sarah. Hey, good morning, everyone. I'm Nathalie. As Sarah says, I'm at the Anton Pannenkoek Institute for Astronomy at the University of Amsterdam, where I'm an assistant professor at present. And for the context of this conference, I was asked to talk about accretion and ejection in X-ray binaries. This is, of course, a very broad topic. And when I sat down to start preparing this talk and looked at the program, I realized that, of course, the entire conference is about accretion and ejection in X-ray binaries. So it was a little bit challenging to find the topics that were not already covered by many other detailed talks. So what I settled for in the end is to highlight a number of detections of disk winds and jets that are occurring in unexpected situations. And in particular, that's from an observer's perspective. As I think I will show you, is that we have some examples of disk winds and jets that we're now detecting that are unexpected for an observer, perhaps, but maybe not necessarily for a theoretician. All right, so just to give you a heads up, I'll post my takeaway message right away. What I hope to be showing you is to highlight that we have increasing examples of disk winds in situations that are sort of against our observational paradigm that we've had for the past 10 or 15 years or so. In particular, we're starting to see more and more disk winds during accretion states where we also see prominent radio jets. And I think we also have a couple of examples now where we see disk winds in X-ray binaries that have very short orbital periods that should be too short to launch thermal winds. So these might be very nice examples of unambiguous magnetic disk winds. And the second thing that I wanted to highlight is that we have new type of jet source in town. These are neutron stars with strong magnetic fields that until recently were actually thought not to be able to launch jets, simply because due to their strong magnetic fields, they're pushing out the accretion flow so far that it was thought that they wouldn't be able to accelerate material into a jet, but apparently they do. Of course, for this conference, there's no need to introduce X-ray binaries. We all know what they are. Just to provide some context, I want to touch upon a few basics that are important to understand the rest of the talk. So just starting with the different wavelengths of X-ray binaries, where they are originating from. Of course, the X-rays, which are most prominent, are coming from the hot inner part of the accretion disk. But in this accretion disk, as you move outwards, the temperature decreases, and therefore also the energy at which you're dissipating, the wavelength at which you're dissipating your energy changes. So the cooler outer parts of an accretion disk are radiating at optical, UV, and infrared light. Now, the collimated jets that we see from many X-ray binaries, they're most prominently detected in the radio band, but we also detect them at shorter wavelengths. So, for example, optical and infrared. Now, I'll be mostly talking about low-mass X-ray binaries. So these are systems with late-type companion stars. They do emit intrinsic UV, optical, infrared emission. But in general, when the X-ray binary is active, this companion star will be completely outshined by the accretion process, so by the disk and by the jets. I just wanted to point out that on all these different components of X-ray binaries, there's many excellent talks throughout the conference. I'm just highlighting a few of them that are directly relevant. All right, so the second point that I want to make for the introduction is that, of course, we all know there's a strong connection between the properties of how the material is flowing inwards, so the properties of the disks, and the properties of the outflows that we're creating, so both the disk winds and the jets. And furthermore, we know that X-ray binaries are observed over a very wide range of accretion rates, so we see the accretion flow change alongside. And the point that I wanted to make is that with changes in the accretion flow, we also observe changes in the outflow, so both in the jets and in the disk winds. So one nice way in which to illustrate this is to simply show a generic light curve of a transient X-ray binary, where you see that the X-ray luminosity increases by orders of magnitude when an outburst starts, and it stays bright for a couple of weeks, couple of months, and then we see it dim out again. So as a population, we see X-ray binaries over a very wide range of accretion rates, all the way from about the Eddington limit down to a very tiny fraction of it. So I'm just gonna step through this plot and show you what different types of outflows we see in roughly different accretion regimes. So starting at the very highest accretion rates around Eddington, maybe up to several tens of % of Eddington or so, this is where in the X-ray spectra we see very prominent emission from the accretion disk. And this accretion disk is apparently coming very close to the black hole neutron star. Now, just during this soft, bright disk states that we also detect disk winds. Now, how we detect these disk winds, just very briefly, because there's also an overview talk on disk winds by Joey Nielsen on Thursday. In case of disk winds, we typically don't observe direct emission from the wind itself. Instead, we're looking at some kind of primary emission source, which is probably likely the disk, like the X-rays or UV, optical, and so on. And then we look at that primary X-ray source through the wind. So the wind is creating absorption features in our emissions, in our continuum spectra, of which you see a nice example shown over here. Now, these narrow lines that you then see, these absorption lines from the wind, they might have velocity shifts, so blue shifts, or they might even show P-signet profiles, and that then tells you about the velocity of your plasma, so the velocity of the wind. Now, from a theoretical perspective, very briefly, there's 3 different ways in which we may launch at disk winds. First one is thermal driving. So due to your X-ray emission from the central source, you're heating the atmosphere upper layers of your accretion disk, and they may reach thermal velocities that allow material to be lifted off the disk and escape in the disk wind. Now, within our current understanding, you need sort of a minimum disk size in order for this to occur, because you need to be able to accelerate the material so that it can escape. So very roughly speaking, if you have accretion disks that are larger than about 4 hours or so, then your accretion disk is large enough to be able to reach that point and drive a thermal wind. Now, at present, we have, say, 1 or 2 dozen of X-ray binaries in which we observe these outflowing disk winds. And the far majority of those seem to be consistent with this thermal driving mechanism. There's quite some debate on particular sources, whether they might need magnetic driving, but this is a large point of debate. So most often people turn to the thermal driving mechanisms. It seems to work for most X-ray binaries. Then again, of course, magnetic driving should be operating at some level, right? Because we have accretion disk, there are threaded magnetic fields. There's various ways in which this should be able to drive magnetic outflows. So the question is then, how does it compete with this thermal driving? So is one of the mechanisms dominating over the other or not? And how can we actually distinguish them from each other? And then finally, in principle, you should also be able to launch disk winds via radiative processes. But in general, it's believed that this is not effective in X-ray binaries, perhaps only at their highest mass accretion rates, which we don't observe very often. Okay, so those are the disk winds that we see at the highest accretion rates. Then if you drop a little bit in accretion rate, so you go to a few percent, maybe a few tens % of Eddington, this is where the disk becomes less dominant in the X-ray spectrum. Instead, we're starting to see this hard X-ray emission from a corona very prominently. And it is during this state that we actually don't see the X-ray winds anymore, and instead we start to see radio jets very prominently. So this is the hard state, or the radio jet state, let's say. Now then, if we go even lower in accretion rate to below 1% of Eddington or so, it becomes increasingly difficult to study the accretion geometry in the outflow, simply because systems become so faint. So very likely the disk is starting to truncate away from the black hole or the neutron star, and we might still produce outflows, both jets and disk winds. And then at the very bottom, at the very lowest accretion rates in quiescence, presumably there's very little matter being accreted, but we do still see outflows. So for example, there's a couple of nearby black holes that are in quiescence, but that still show radio emissions. So apparently they're still launching radio jets. And from Guillaume's talk yesterday, we saw that, that also in quiescence, you might expect to be producing winds. It's just very hard to actually detect them. Now, from this picture I'm sketching, you can already you can already start to grasp that there seems to be this observational paradigm that we don't detect X-ray disk winds and radio jets at the same time. For some reason, they seem to be mutually exclusive from an observational perspective. And this was borne out by a number of nice papers about 10, 15 years ago that highlighted this, this apparent non-simultaneity. However, this is the observational paradigm that is now slowly starting to change, and I want to highlight a few examples that show that. So I will start off by this particular X-ray binary. This is a neutron star called XrB 7059. It's a transient, had an outburst in 2018, and this happens to be an accreting millisecond pulsar, which means that its magnetic field is strong enough to channel some of the material from the accretion disk onto its magnetic poles to create outflows. Now, this was not particularly X-ray bright, accreting around 1% of Eddington or so. So this is in the regime where you normally expect radio jets. And this source did show radio jets. This is very nice work by Tom Russell, which did a radio study of this source. And here you see this famous diagram of the radio luminosity versus the X-ray luminosity with a large sample of black hole and neutron star X-ray binaries. In this plot, the black holes are the black dots and the neutron star X-ray binaries are the gray dots. And here in colors is this particular source indicated. So it had a radio jet and it also had an extremely bright radio jet. You can focus on the orange squares over here. This neutron star was detected all the way along the black holes. Now, what's interesting is that around the same time that we had this radio jets detections, there was a separate study led by Mike Novak of Chandra data of this source. And you see a snapshot of this data here. And they were actually detecting narrow absorption lines that were blue shifted, and that indicated that there is also a disk wind present in this source. So it's in a typical radio jet state. We do see a radio jet, but apparently there's also a disk wind at the same time. I think this wasn't really picked up because these were separate publications, but I think this is a very interesting example where you have quite a regular system. We have both jets and X-ray disk winds at the same time. Now, this neutron star is not alone. This is another example. This is a black hole, Maxi J1820. I think many of you know this black hole. Had an outburst in 2018. Was not particularly bright. It did reach soft states, so disk states as well, but it was also in a hard state in a radio jet regime for a long period during its outburst. Now, the group of Theo Munoz Darius in Tenerife, they detected both optical and near-infrared disk winds from this system throughout its different states, so both in the soft state and in the hard state. And here's a nice example from their infrared wind detections, where you see two line profiles, and there's a very nice P-Cygni profile in one of them. And this was in a hard state, so when we also see radio jets from the system. Now, this black hole is not alone. Theo and his group are doing many of these studies, and they're finding optical and infrared disk winds in black hole systems all over the place, all in radio accretion regimes. So it seems that it's really not uncommon that these disk winds are there in radio states. We just haven't been finding them before. Now, it is my understanding that also from a theoretical perspective, this is not unexpected. So, for example, from the simulations of Sarah Markov's group by, for example, Kaushik Chatterjee, or also by Matthew Liska, what I understand from them is that you actually need these winds to be there in order to collimate your radio jets. So it shouldn't be surprising, at least from a theoretical perspective, that we start to see these disk winds in radio states now as well. We just hadn't been finding them before. All right, so that was the first highlight. Then the second one that I wanted to highlight is that we're starting to see examples of disk winds from very small accretion disks. This is my first example. This is a neutron star called J1804. Had an outburst in 2015, and it was a very nice outburst. Showed various different state transitions, very nicely described by Alessio Marino, who is also talking later in this session about another source, I believe. Now, this particular neutron star was quite bright, so it reached what we call a soft state. So you would expect disk winds in this system simply based on that, and this is indeed what we saw. Here's an example from Chandra data from this source, where you see at low energies you see these very prominent narrow absorption features, and they are also blue shifted. So this suggests that there is a clear wind detection in this system. And this is actually a work that was started off by an undergrad at the University of Amsterdam, and we're currently preparing this to write up. Now, since this source was in this disk wind regime, in principle, we shouldn't be surprised that there was a disk wind. But what is so interesting about this particular source is that there's quite strong evidence, both from X-ray and optical properties, that it should have a very small accretion disk. For example, a very nice paper by Cristina Baglio on this source, pointing out that it likely has an orbital period less than about 1.5 hours. So if this system truly has such a short orbital period, you would expect that it shouldn't be able to launch thermal winds. So maybe this is a very nice example of a system where you have an unambiguous detection of a wind that must be magnetically driven, perhaps maybe with some contribution from radiative processes. Now, there's a second source that I wanted to highlight, for which we conclude sort of the same. This is again a neutron star, but then in a very different accretion regime. So this one is accreting at much lower accretion rates, even below 1% of Eddington. Now, this happens to be a neutron star that is persistently accreting. It's very faint though, and this is also an accreting millisecond pulsar. So we know from the pulsations its orbital period, and it's very short, around 40 minutes or so. Now, because this source is accreting at such low luminosity, we're really pushing sensitivity limitations of our X-ray instruments, but still we might be seeing a disk wind in this system too. Here's an example from one of the studies that we did where we tried to search for these narrow lines. And we see a couple of lines that are low significance, 3, 4 sigma, but they do seem to be there, and they might suggest that there is a wind here. Now, what sort of supports the idea that there might be a disk wind here that is losing mass comes from modeling the optical, infrared, UV spectral energy distribution of this source, which you see over here. This is work done by Juan Hernandez Santisteban, and from his modeling, he concluded that from the optical infrared, you can estimate what kind of mass must be flown into the disk. But then it appears that less than 90% of this is not coming out as X-rays. So it seems that somehow this system is losing a lot of mass along the way. So one way to do this perhaps could be a disk wind. So maybe this is what we're seeing in our X-rays. Maybe this is again another example of a source that must be launching a disk wind via magnetic processes. Now, the reason that I wanted to highlight this source is that there is also indirect evidence for a similar type of system, so other accreting millisecond pulsars that have small disks that from their orbital period evolution seem to be losing a lot of mass as well. So mass transfer seems to be very non-conservative in these systems. This is, for example, work done by Tiziana Di Salvo and Alessio Marino as well. So maybe all of these systems are losing a lot of mass via disk winds that we just haven't detected yet. All right, so that was from the disk winds that are unexpected perhaps from an observational perspective. Now just briefly highlight also some unexpected jets, and these ones are, I think, unexpected both from theoretical and observational perspective. So very simply put, when we think about jet launching, there's these two main models that we've had for decades. On the one hand, you might be launching a jet by extracting energy from the event horizon of a black hole, the Blanford-Signac model. On the other hand, you might be launching a jet from magnetic fields in your accretion disks. And this is a process that, of course, should work for both black holes and for neutron stars. Now, in case of neutron stars, it's good in the context of jet launching to realize that there's two types of neutron stars, basically. On the one hand, we have neutron stars that have relatively low magnetic fields, 10 to the 8 Gauss or so. And these typically have quite rapid spin periods on the order of milliseconds. On the other hand, we have neutron stars with strong magnetic fields. So those are mostly in high mass X-ray binaries, so relatively young systems. And their magnetic fields are something like 10 to the 12, 10 to the 13 Gauss or so. And these neutron stars are typically spinning slower, on the order of seconds to minutes or so. Now, it is these strong magnetic neutron stars that should have a very strong effect on the accretion flow. In fact, their magnetic field is likely strong enough to push out the accretion flow, either thick or thin, out to distances of hundreds of gravitational radii. So in these systems, matter is not supposed to come very close, at least in some kind of disk form, to your neutron star. Now, it is for this reason that it was thought for a long time that these systems shouldn't be launching jets. And this was first borne out by observations. So when radio observations of X-ray binaries took off, every time there were radio observations of a neutron star with a high magnetic field, there were no radio detections. So this started off as an observational paradigm that these strong magnetic field neutron stars should not be able to launch jets, but there's also some theoretical precedent for this. For example, pointed out in a theoretical work by Massi and Kaufman Bernardo, 2008, and they just pointed out that because you're not able to get your accretion flow so close to your neutron star, you shouldn't be able to launch jets, at least not via the Lanford Payne mechanism.
Natalie, 5 minutes.
Yes, perfect. So this is another observational paradigm that started to change very recently, only about 2 years ago. And it changed with this particular source. This is called, the source was called SwiftJ 0243. This is a high magnetic field neutron star that was newly discovered in 2017 when it had an outburst. So what you see here in gray is the X-ray outburst of this system. So you see this very nice outburst that lasted for a few hundred days. And what you see in red and in blue are radio observations of this system in different frequency bands. And in the bottom plot, you see the radio spectral index. So when the outburst was rising, we didn't detect any radio emission, but we did start to detect radio emission from the peak of this outburst. And we saw this radio emission also evolve in tandem with the changes in X-rays along the outburst. So this is work that was published by my former PhD student, Jacob van den Einde, who is now an independent postdoctoral fellow in Oxford. And this was the very first unambiguous detection of an evolving radio jet from a neutron star with a high magnetic field. Now, there's such a thing as a discovery bias, of course, but this source does not stand alone. So Jacob has done an amazing job of also studying other neutron stars with high magnetic fields in the radio band and finding several other radio detections in such systems. And this is illustrated in this plot here, which is again radio luminosity versus X-ray luminosity. In this plot, the black holes are the gray crosses, and then the neutron stars with low magnetic fields are the black points. And the neutron stars with the high magnetic fields are all the red squares in here. So you see the one that we initially detected, SwiftJ 0243 over here, and then we have several other of similar systems that are detected too. You also see a lot of upper limits for these systems, and I think this just illustrates that we're hitting the current sensitivity limitations of the radio instruments for these kind of systems. And another thing that you can take away from this is that at least at some X-ray luminosities, these systems seem to be much fainter in radio than low magnetic field neutron stars and then black holes. So this is a new source of new jet source in town that is very interesting and provides new regimes to probe jets from X-ray binaries. All right, so. This brings me to my wrap up. There's of course many open questions about disk winds and jets in X-ray binaries. I'm just posing a few of them. One of the questions that I am interested in is what is exactly the dominant disk wind driving mechanism? So how do magnetic and thermal processes compare? I think from that perspective, it's interesting that we're starting to see some disk winds in X-ray binaries with short orbital periods that might presumably need magnetic driving in order to explain them. And something that I didn't show, but that's also interesting, is that neutron stars show thermonuclear bursts, which are brief instances during which they emit X-rays near the Eddington limit. And there are a few cases in the literature where we might see disk winds that are temporarily being launched by these processes, presumably due to radiative driving. One open question that we still have, we're starting to detect these cold optical infrared disk winds from X-ray binaries now, but how do they relate to the X-ray UV disk winds that we've been studying for the past 20 years or so? Are they part of the same outflow, or are they actually different phenomena? And of course, the main question about disk winds is also how much mass do they contain, and is this mass lost from the system? So can disk winds be a cause of highly non-conservative mass transfer in XrB binaries? And then finally, from jets, I think it's exciting that we have this new type of jet source in town. And it's still an open question how these high magnetic field neutron stars can launch jets, and also what causes the differences in radio brightness between different types of neutron stars and black holes. All right, I will stop here, leaving you with the takeaway message that I already posted at the start of my talk. Thank you.
Thank you very much, Natalie, for the excellent talk. And I see already a question from Asaf. So just to remind you, please, well, Asaf, you can introduce yourself again for those who weren't here yesterday. But then for those of you in the room, let me know if you have questions as well. Go ahead.
Yeah, there are questions here. So after the.
Okay.
So, well, thank you very much for an excellent talk. I have a question to clarify. You mentioned that the winds are needed in simulations in order to launch jets. But then I think that you mentioned that they were only observed during the high soft state. So my question is, are there any evidence for winds during the low hard states, or none exist to date?
Yeah, so that was what I was trying to point out. So we're starting to see more and more examples of those now. So there's a handful of X-ray wind detections in the low hard state, I think, and also so Tenyo Muñoz-Darius and his group are starting to detect these optical infrared wave disk winds in low hard states.
So they do exist?
Yeah, we're only starting to discover them now, like say in the last 3 years or so. So until recently, we thought they were not there. We didn't see them.
All right. And are the properties the same as those in the high soft state, or different properties?
Oh, so at least like, for example, one of the things you can look at is of course the outflow velocity, and that seems to be very similar between the different states. And also in one of the black holes 1820, where they look at the infrared wind, it actually hardly changes between the soft state and the hard state. So it seems to be rather constant throughout the outburst, which is interesting.
All right, thank you.
Okay, so let's jump to someone in the room, and then we'll come back online. And awkwardly, please look at the camera at us. Yeah, okay, thanks.
Hi, Natalie. Thank you for the nice review. I wanted to ask you if we are absolutely certain that the radio emission seen from high magnetic field neutron stars comes from a jet, because radio emission does not necessarily imply a jet. It could come from lots other sources. So are we absolutely certain? Have we seen spectra of a compact jet, for example? How do we know it's a jet?
Yeah, of course, perfect, viable question. And this is also what we're addressing in all the works that Jacob is doing. So for example, we do have a few systems like, for example, Vela X1, where we cannot exclude that the radio emission might be related to the wind instead, so the companion wind. In the one that we initially discovered, so Swift J0243, that is the one where we really see the radio spectral index be very consistent with what we see from compact jets in low mass X-ray binaries, and also we see it evolve in the same way along the outbursts as we do in low mass X-ray binaries. It really strengthens the idea that these are truly radio jets. So also for some of the other detections that we have, we can exclude that that the radio emission is, for example, from the companion wind just on the system properties, but there are also a handful where we cannot be exclusive. Yeah.
Okay, thank you. So let's go back online. I think Greg was first, and then I have Jonathan, and I don't know if there's anyone else in the room, but let's just keep going kind of in order or back and forth.
Sorry, there's also a question on Slack as well.
Yeah, right. Okay, actually, let's jump to Slack. I see quickly, thanks for the nice talk. How do these LMXB jets compare with the relativistic jets in AGN?
That's a question that other people can better answer than me. I think I know very little about the relativistic jets in AGN.
Yeah, maybe we can come back to that in the discussion. I mean, for one, they're a bit slower, but okay, great. So let's go to Greg then.
Sure. So Natalie, in your takeaway messages, you point out that we're tending to see the compact radio, we're tending to see the disk winds in the compact radio jet state when there are short orbital periods. Do you think that's actually astrophysical, or do you think this is really a selection bias at play?
Yeah, so there's been a number of works also indeed to so whether we might not be seeing these disk winds at some places because of observational properties, right? Like ionization, for instance. So I think that we have some attendants like Stefano Bianchi that did some nice work on this, right? Yeah, so observational effects are probably related to this as well. Yeah, I think.
Thanks.
So we're running out of time. Do we have a short question in the room, Pop?
Yeah, one.
Okay, let's do one last one quickly.
Hi, Natalie. Ilek here. My short question was given, so independently from independently from the launching mechanism of the jets, if we assume that it's powered by the rotational energy of the neutron star, is the power of the jet high enough to induce significant spinning down of the neutron star, like measurable?
That's a super interesting question, of course. I don't know based on calculations, but it's one of the things that we have in mind to try and probe with observations. So for example, of course, neutron stars can go through phases of spin up and spin down. So if indeed this is related to that, we should see differences in their jet properties, I think, between spin up, spin down phases. So this is something we have on our list to try.
Okay, thanks.
All right, well, thanks again, Natalie, for the talk and the